In the last video, we talked about how to use the leading term of a polynomial to determine its end behavior, which gives information about what the long-term behavior of the function is like, whether it gets very, very large in the positive or negative direction as x gets very large in the either positive or negative direction. This is very essential for understanding what happens to the function when x is very, very large, but it doesn't give any insight into how the graph of the function behaves when x has more moderate values. In order to understand that, we have a few places that we can go, but the most important one is understanding the intercepts of the function. So that's what we're going to look at today, intercepts of polynomial functions. And we know that there are two different kinds of intercepts, the X-intercept and the Y-intercept. Now the Y-intercept of a function is fairly simple to find, just like for ordinary functions. The Y-intercept is straightforward, so we're going to take care of that, talk about it quickly, and then not come back to it until we have some examples to work on. However, the X-intercepts we have to do a little more with, and they actually give, in many ways, a lot more of an important look into how the function actually behaves. So, first of all, the Y-intercept occurs at the point 0, f of 0. You plug the value 0 into the function, you get a number out of it. That is the y-coordinate of the point on the graph with an x-coordinate of 0. That is your y-intercept. And that's all there is to it. You plug 0 into the function and you get your answer. So let's move on from there to x-intercepts. To find the x-intercepts, we usually want to factor. Now we're talking about polynomial functions here, so functions where you can write down the formula for f as a polynomial. Now polynomials will often factor, and when we can factor it, that will tell us how we can that'll tell us the zeros of the function, or the x-intercepts, because the following. So we recall that the x-intercepts occur when f of x equals 0. The x-intercepts are the points on the graph that lie on the x-axis, and the points on the x-axis are precisely those points that have a y value of 0. That is where the output of the function is 0. So we want to find the x-intercepts that occur when f of x is 0. Now when f is a polynomial function, then f of x is a polynomial, and so solving the equation f of x equals 0 is solving a polynomial equation, which typically involves factoring. So let's suppose that we have factored, or maybe we're lucky enough that a function has already been given to us in factored form. And I want to take an example because there are actually 3 different ways that the function can have an x-intercept, 3 different kinds of x-intercepts. Technically, we could break them down further, but those three are the important ones that we want to care about. So let's look at the function f of x equals -1/3 times x plus 2 times x plus 1 cubed times x minus 3 squared. Now this is a polynomial function. It's not currently written in the polynomial form, the standard polynomial form that we have seen, but you could multiply all of this out to get that form. Now multiplying it all out would be a bit of a pain. This is a degree 7 polynomial, which is pretty large and complex. However, what I care about are these factors. these factors give us the x-intercepts because we've actually already seen this often when solving equations. If we set this expression equal to 0, then the fact that we have these three factors all multiplying together to give us 0 means, by the zero factor theorem, that one of them has to be 0. So this occurs if x plus 2 equals 0, or x plus 1 cubed equals 0, or x minus 3 squared equals 0. So each factor gives us one x-intercept. And so let's see how that goes. Continuing this process, so if x plus 2 equals 0, then that means that we can solve this for x and say, okay, well that means that x has to equal -2. Now if x plus 1 cubed equals 0, then that means that x plus 1 has to equal 0, because the only number whose cube is 0 itself. Now we can subtract 1 from both sides of this equation to get x equals -1. Similarly, if we have x minus 3 squared equals 0, that means x minus 3 has to equal 0. That's the only way. The only number whose square is 0 itself. And therefore, we have that x equals 3. So we get 3 x-intercepts. One coming from each of these factors here. However, there is some difference between them, and it has to do with the power that appeared on each one of these factors. So we've got a power of 3 that appeared on the factor x plus 1, a power of 2 that appeared on the factor x minus 3, and there's an invisible 1 sitting as the power of the factor x plus 2. These numbers are important. These numbers are going to determine what we call the multiplicity of each of these intercepts. So, for instance, we will say that the x-intercept at -2 has multiplicity 1. And that's because the factor x plus 2, which gave us that 0 of -2, occurred once in the factored form of the polynomial for f. On the other hand, the x-intercept given by x equals -1 came from the factor x plus 1 cubed, and so here we'll say that this has multiplicity 3. And lastly, we have the intercept x equals 3, which has multiplicity 2. And it turns out that the multiplicity of a 0, or of a factor, which gives us an x-intercept of the function, determines how the function, or how the graph of the function reaches the x-axis at that point. So let me write things down in a slightly more precise form in a definition, and then we'll look at how these multiplicities actually affect the graph. So definition. If the polynomial function f is written as f of x equals some number a times x minus b1 to the m1 times x minus b2 to the m2, etc., down to x minus b to the mk, then f has an intercept at b1 of multiplicity m1, an intercept at, or I should say an x-intercept at b2 of multiplicity m2, and so forth. So if we can write down our function this way, if we can factor it completely as some number times x minus something to a power times x minus something else to a power times etc., then we can immediately read off all of the x-intercepts of the function f and their multiplicities. Now, the reason why the multiplicities matter is because they determine what the graph looks like at that x-intercept. So, we're going to be describing the possible ways that the graph can reach the x-axis by splitting them up into three categories. So, let's consider an intercept with multiplicity 1, an intercept with even multiplicity, and an intercept with odd multiplicity, but greater than or equal to 3. So, in cases where we have a multiplicity of 1, the graph of f is going to pass straight through the x-axis. It's just going to go right on through, not going to pause or anything. However, if the particular intercept of the function has even multiplicity, that is multiplicity 2 or 4 or 6, etc., then the graph is going to come down, it's going to reach the x-axis, but it's going to go back up. It's going to come up, it's going to touch the x-axis, but it's not actually going to pass through. So this is like the graph of y equals x squared. This multiplicity 1 is like the graph of y equals x, a linear function that just passes straight through. Even multiplicity has an intercept that looks like the graph of y equals x squared, the parabola, and an odd multiplicity function has a graph that looks like y equals x cubed. Now that means that the graph is still going to go through the x-axis, but it's going to flatten out as it does so. So if an intercept has a multiplicity that's odd but is greater than 3, or greater than 1 rather, 3 or greater, then it's going to flatten out when it reaches the x-axis before continuing on its way. So these are the three different kinds of intercepts that a polynomial function can have. It can either go straight through with multiplicity 1, it can come down, touch the x-axis, but then bounce off if that intercept has even multiplicity, or it can have an odd multiplicity where the graph comes up, touches the x-axis, flattens out, but then keeps going in its same direction. And we can use this information, this pattern of what the multiplicities of intercepts of a function look like, in order to graph out functions that we look at. We can combine this information with the end behavior in order to get a reasonably complete picture of the graph, especially when we combine information about the y-intercept with it. So let's return now to our previous example. Let's look at f of x equals -1/3 times x plus 2 times x plus 1 cubed times x minus 3 squared. Now, when the function is written out in factored form like this, we can identify the intercepts and their multiplicities immediately. So we can see from here that we have an intercept at -2, because if we plug -2 into this factor, we'd get 0. And we see that it has a multiplicity of 1, because this factor of x plus 2 has a power of 1. It appears exactly once in the factored form of f. Now, for the next one, we have an x-intercept of -1 with a multiplicity of 3. And then finally, we have an x-intercept of 3 with a multiplicity of 2. So we can start our graphing process by identifying these places and noting them. However, we won't have a complete idea of the behavior of this graph until we get a little bit more information, but we can do some of these. So we see that we've got an x-intercept at -2, and let's see, I'm actually going to double up on the notation here because of what the numbers in our problem look like. All right, so we know that we have an x-intercept at -2, and it has a multiplicity of 1. Now that means that we know that the graph is going to go straight through this, but we don't know whether it goes through like that or like that yet. There are two different ways that we could have a multiplicity 1 intercept. We don't know which one it is, so we're going to go ahead and leave it for now. We'll just remind ourselves that this has a multiplicity of 1. We don't need to use this notation here, but it can be helpful. Now, the 0 at -1 has a multiplicity of 3, and we've got third intercept at 3 with a multiplicity of 2. Let's see what else we can tell about this function that will help us to graph it out. So let's look for the y-intercept. For the y-intercept, we want to plug 0 into the function. Now, when the function is all factored like this, plugging in 0 is not too difficult because each one of these factors we can just plug 0 into. So we get -1/3 times, and then 0 plus 2 is 2. And then 0 plus 1 is 1 cubed, and then 0 minus 3 is -3 squared. So that's what we get when we plug 0 into the function. We can simplify this down. We get 2. 1 cubed is just 1, so we can forget about that. -3 squared is 9, so we get 2 times 9, which is 18, which means we get -6 out of this. So f of 0 is -6, so that means that the point 0, -6 is the y-intercept. So we can go ahead and graph that down here. So this is the point 0, -6, y-intercept. Okay, and then the last thing that we want to figure out is the end behavior. Now for that we need to look at the leading term. Now the trick here is that if we look at -1/3 times x plus 2 times x plus 1 cubed times x minus 3 times x minus 3 squared, we can find the leading term by removing all of the constants that are being added to x's in each one of these factors here. When x is very, very, very large, we can't. Then adding the 2 or adding the 1 or subtracting the 3 makes very, very little difference. And so the leading term of this function is actually obtained by just ignoring all of those and looking at what we get out when we take those away. So that means that the leading term is actually -1/3 times x cubed and times x squared after we remove all of the numbers that are being added or subtracted to the x's. So that's going to give us -1/3 times x to the 6th. I think I said it was a degree 7 polynomial earlier. That was silly. It's degree 6 polynomial. So from this, we can determine its end behavior. So because the leading coefficient is negative, we know that the function has an end behavior which falls to the right. That's what a negative leading coefficient does. And then because the leading term has even degree, that means that the end behavior on the left and right hand side of the function are the same. So that means that the function has an end behavior that looks like this. It falls to the left and falls to the right. Okay, so now that we've put in all this information, we've got the intercepts, we have the end behavior, we're actually ready to sketch out the behavior of this function. Now, making sure that you've got the multiplicities correct here is very important. If you mess them up, then your graph obviously is not going to be completely correct. Sometimes your graph will just break and you won't have a way of doing it if you've messed up the multiplicities. So make sure and be careful about that. But let's do this one. So I like a lot of times just moving from left to right. So I know where my function starts. It starts down here based on the end behavior. So then it's going to come up and I'm going to start heading towards my first 0. So here's my first 0 and I think, okay, well, what sort of multiplicity does it have? I've noted here that it has multiplicity 1, which means that the graph is going to go straight through the x-axis as it passes through this x-intercept. And now I see that I got another x-intercept very quickly, so I'm going to have to turn back around. Make sure that the graphs that you're drawing always still, obey the vertical line test. You don't ever want to come back on yourself like that or something. That's not the graph of a function. But this x-intercept has multiplicity 3, which means I need to flatten out and then keep going back down like this. All right, the next point, reading from left to right on the graph that I know I have is this this intercept down here where x is 0. Now, I don't actually know at this point whether this point 0, -6 is a local minimum or not. It might be, but it might not be. Furthermore, I don't even know whether the function is increasing or decreasing at this point. Figuring out those details can most easily be done by using a computer to graph this out and getting a good sense of what the graph looks like. If we want to do it by hand and get more precise information about where the function has its local maxes and mins and stuff like that, actually that's where we need calculus. We're only going to be able to approximate it here, but that's okay. I like to just sort of go smoothly through. And this is a guess. It's really just giving very general information. And then I'm going to come up here, and now this 0 has multiplicity 2, which means I know I'm going to touch it, bounce off, and then come back down, eventually meeting up with my end behavior arrow that I had down there. And so this is approximately what the graph of this function f looks like. It's fairly crude. It's only giving the broad idea of how this function behaves. We have very specific information about a few points. We know where the intercepts are, and that's about it. But then we know lots of big picture information. For instance, one thing that we do know is that there's some local max. There's some local maximum here for some x value between -2 and -1. We don't know what it is, but we know that it exists there. And so if a local maximum has relevance to whatever problem you're working on, you know that one exists there, and you can go looking for it or use that information somehow. We can also see that, of course, there has to be a local minimum somewhere here between the x values of -1 and 3. We don't know, again, exactly where it is, but we do have that information. One thing I do want to point out here that is occasionally relevant is we can look at the total number of times that the graph turns. That is, the total number of times that it goes from being positive, rather increasing to decreasing, or vice versa. In other words, we can look at the total number of local maxima and local minima of this function. In this case, we can see that we have 3 of them, at least 3 of them. We don't know, we don't have a whole lot of information about what this function does, especially between -1 and 3. There could be other things in here. So for instance, the function might do something weird like this, in which case we might have 2 more extrema here. We don't have the tools at hand to determine whether that happens or not. So for the moment, I'm just going to connect things up simpler. However, we do know that it can't get too complicated. There's a general rule that can help us in understanding how the graph of a function looks. Or in another way of looking at it, we can sometimes tell something about the function from the graph. So we have the following rule. The total number of turning points or in other words, local minima or maxima, places where the function turns from being increasing to decreasing or vice versa, is at most 1 less than the number, or sorry, 1 less than the degree of the rational function, or polynomial function, sorry. So what does that mean? It means that if I take some function f here, and let's say that it has degree 5, 3x to the 5th minus 7x squared or something like this. That means that when I graph this function, well, first of all, end behavior has to look like this, but it could get complicated inside. So this function can have at most 4 turning points. At most 4 points where it switches from being increasing to decreasing or vice versa. So it could look like this. There's 1, there's 2, there's 3, there's 4. So that's fine. A degree 5 polynomial could have a graph that looks like this. However, it could not have a graph if I add in some more. If I add in that, it could not have this graph, because notice that this graph has 1, 2, 3, 4, 5, 6 turning points. And so it could not be the graph of a degree 5 polynomial function. One way that we can use that is to say, suppose that we have the graph of a function. We're told that this is a polynomial function. And we can ask, what can we say about it? Well, there's actually quite a lot we can say about this polynomial function. For instance, by looking at the end behavior, falling to the right and the left, we can see that this function has even degree. It has negative leading coefficient. And we can determine a bound on its degree by counting the number of turning points it has, or local maxima and minima. So this one has a bunch of them. I'm circling the approximate locations where all of the maxima and minima are. I want to make sure I haven't missed any. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 turning points this function. So that means that the degree of this function must be greater than or equal to 16, because this graph has 15 turning points, and so a polynomial function with that graph must have degree at least 16. So let's move on and do a couple more examples of graphing functions based on their intercepts and end behavior. Let's graph or sketch the graph of f of x equals 5x to the fourth minus 10x cubed. Now, this function, unlike the previous one, hasn't already been factored. In that case, you want to factor first, if at all possible. So f of x is equal to 5x to the fourth minus 10x cubed. And if we factor, we can see we can factor out 5x cubed and then times x minus 2. Now in this case, there are two factors that are going to give us x-intercepts. The variable x by itself is a perfectly good factor. Now x equals x minus 0. So this factor right here, x cubed, is going to give us an x-intercept at 0 with multiplicity 3. The factor x minus 2 is going to give us an x-intercept of 2 with multiplicity 1, because there's an invisible 1 sitting on this factor here. Furthermore, we can look at the end behavior. We have the leading term is 5x to the fourth. So because it's got a positive leading coefficient, we rise to the right. And because the degree of the leading term is even, that means that we do the same thing on the left and the right. So this is going to rise to the left as well. Last thing we need is the y-intercept. Y-intercept is easily found. F of 0 is equal to 5 times 0 to the fourth minus 10 times 0 cubed gives us 0. So that means that the point 0, 0 is the y-intercept. So let's graph this function, and we'll see that in this case, we're really going to need an additional piece of information to really make sure that we've got a good idea of what this graph is doing. So we've got, let me go ahead and label. I've got 0. We'll go ahead and do 1, 2, 3, -1, -2, -3. So we have an x-intercept at 0 with multiplicity 1, and we have an x-intercept, with multiplicity 3, and an x-intercept at 2 with multiplicity 1. And we know that our end behavior is that we rise to the left and we rise to the right. Let me go ahead and move this Y-intercept computation away, or out of our way. Okay, and then we've got a Y-intercept at 0, 0, which we actually already have noted. Now, we can go ahead and sketch things out already, but one thing you'll notice is that all of the points that we have written now lie on the x-axis. What this means is that when we sketch this out, we won't really have a very good idea of the sense of vertical scale that we're dealing with in this problem. So what I like to do in situations like this is to find one or two other easy points to plot that aren't zeros of the function, just so that we can get some more information, some more picture of what's going on here. So let's go ahead and get some other points. I'll go ahead and plug in x equals 1 and x equals negative 1. So if x equals 1, then we have that f of 1 is 5 times 1 to the 4th minus 10 times 1 cubed, which gives us 5 minus 10, which is negative 5. So that tells me that the point 1 comma negative 5 is on the graph. But before sketching it out, let's do the other one so that we know what scale of numbers we're looking at. So we've got 5 for x equals negative 1. F of negative 1 is 5 times negative 1 to the 4th minus 10 times negative 1 cubed. Now this is going to give us 5. Negative 1 to the 4th is just 1. But then negative 1 cubed is negative 1. And negative 10 times negative 1 will be positive 10. So we get 15. So the point negative 1 comma 15 is also on the graph. So rather than trying to make our graph huge, I'm just going to go ahead and adjust the vertical scale of this graph so that each of these marks corresponds to 5. So this is going to give me 2 more points on the graph. Got 1 comma negative 5, and I have negative 1 comma 15. All right, so now we'll go ahead and do things. And right now it looks like the arrow that I put in for my end behavior on the left is a little too far to the left. That's okay. We can move it. It's mostly just there to remind us, at least at the beginning anyway. So now we can come in and try and graph our function. So we pass through the point negative 1, 15. And now we're going to go through the point 0, the x-intercept at 0. It has multiplicity 3, so we're going to flatten out here before coming down. We're going to pass through the point 1 comma negative 5. Going to go through the x-intercept at 0, which has multiplicity 1, so we go straight through and then up like that. And we can get rid of our earlier end behavior notation. So this is approximately what the graph of this function f of x equals 5x to the 4th minus 10x cubed looks like. Let's do one more example, and you'll see that the general strategy is going to continue to remain. We're going to factor, find the end behavior, find the x-intercepts with multiplicity, and find the y-intercept. So this next one is probably the most complex of the ones that we've seen. So f of x is x to the 4th plus 2x cubed minus 9x squared minus 18x. Now this is a fairly complicated function. It's got lots of terms, and if you encountered a function like this in real life, in an application, most likely it wouldn't factor nicely. Most likely you'd have to rely on just approximating the graph of this using a computer. However, if you're given one in, say, a course or in a textbook, something like this, go ahead and try to factor it, because a lot of times they're designed in such a way that it can be. So let's try ahead and try and do that here. So first of all, we notice we do have a common factor of x. So we get x times x cubed plus 2x squared minus 9x minus 18. We want to continue factoring. Now for the term, for the large degree 3 polynomial term there, one trick that you can often use, which sometimes works with polynomials with 4 terms, is factoring by grouping. So for this, we're going to look at the first set of 2 terms, the x cubed plus 2x squared, and factor out the greatest common factor. In this case, x squared is the greatest common factor, leaving behind x plus 2. And now we have negative 9x minus 18. We want to factor out the greatest common factor there. That's going to be a negative 9. Now, when factoring, you always factor out in such a way that that the first term that remains has a positive coefficient. So we factor a negative 9 out, which leaves an x plus 2 behind. Now, notice that we have an x plus 2 that's common to both of these terms, which means we can actually factor that x plus 2 out of the terms inside the big set of parentheses, and we're left with x squared minus 9 after we pulled the x plus 2 out of both of those terms. Now, of course, that allows us to drop the outer set of parentheses, but we're not quite done. X squared plus 9 can factor because that's a difference of squares. So x squared minus 9 factors as x plus 3 times x minus 3. And so now we can write down all our various x-intercepts. We have an x-intercept of 0 coming from our first factor of x. An x-intercept of negative 2 coming from the factor x plus 2. An x-intercept of negative 3 coming from the factor x plus 3. An x-intercept of 3 coming from the factor x minus 3. And the multiplicity of each of these is 1. Each one of these zeros has multiplicity 1, and so that's what we'll use to graph out the function. All right, to find the y-intercept, we just plug 0 in. So f of 0 is equal to, going back up to the original, we can either go to the original or to the factored form. If we go to the original, we get 0 to the 4th plus 2 times 0 cubed minus 9 times 0 squared minus 18 times 0, which is 0. So our y-intercept is at the point 0, 0. And then finally, the end behavior, our leading term is x to the 4th. The coefficient of x to the 4th is positive 1. So we rise to the right. And then because the degree of this polynomial is even, we do the same thing on the left. So we also rise to the left. So now we've got almost all the information that we need. Let's get one point on the graph that's not on the x-axis the same way we did before, because currently the only points that we have are the x-intercepts, and the y-intercept happen to also lie on the x-axis. So let's just take some number that we don't have listed here. Notice that we've got 0, negative 2, negative 3, 3. I'm going to go ahead and calculate f of negative 1 and f of 1. So f of negative 1, for this I actually want to use the factored form. The factored form is going to be a lot easier here. So f of negative 1 will be negative 1 times -1 plus 2 is 1, -1 plus 3 is 2, and -1 minus 3 is -4. So using the factored form here, we get -1 times 1 is -1, times 2 is -2, times -4 is 8. And then f of 1, so that gives the point -1 comma 8, which is on the graph. Similarly, f of 1 gives us 1 times 3 times 4 times -2, plugging it all again into the factored form of f. And so that gives 1 times 3 times 4 is 12, times -2 is -24. So we have that the point 1 comma -24 is on the graph. So that will help us to calibrate our y values. So let's go ahead and graph this function. So let's see, we need x values out to 3. And then -1, -2, -3. And then let's see, for y values, we need to go up to 8, down to -24. Let's see, can I do 4? Yes. 4, 8, 12, 16, -4, -8, -16, -24. Your scales can be different on your x-axis and your y-axis, but along a given axis, they need to remain consistent. Okay, it's now some time later. Apologies, my computer crashed as I was recording this section, and then I tried re-recording it, but there was an issue with the sound. So doing this now for the third time. Apologies for the video going up late. So we were in the middle of graphing this polynomial function, f of x equals x to the fourth plus 2x cubed minus 9x squared minus 18x. And now that we have the x-intercepts with their multiplicity, the y-intercept, the end behavior, and a few more points, because all of our previous points all lay on the x-axis, we're ready to graph it. So let's go ahead and do that. I'll start by putting dots at all of my x-intercepts. I've got an x-intercept at -3, at -2, at 0, and at 3. And this time I won't note the multiplicity on the graph right now. Well, in this case, all the multiplicities are 1, but I could also just refer back to my table of x-intercepts and multiplicities as I go through the problem and graph it out. The y-intercept is 0, 0. We already have that noted. So let's get our other 2 points. The other points that we have on the graph are -1, 8, which goes right there, and 1, -24, which goes right there. So now we're ready to graph this function. So again, moving from left to right, we start off by looking at the end behavior to see sort of where we're coming from. And we know, based on what we've just done, that the graph of this function rises to the left, which means that way over on the left-hand side of the graph, the graph looks something like this, going up and to the left. So now it's going to come down. We're going to see that it reaches the x-axis at -3 with multiplicity 1. So the graph is going to go straight through the x-axis. Then it's going to come around, and it has to go through the x-axis at -2 again, going through that point because that 0 also has multiplicity 1. Passing through the point -1, 8, passing straight through the graph at 0, coming all the way down to the point 1, -24, coming back up through the 0 at 3, and the end behavior is up and to the right. And so this is a sketch of what the graph of this function looks like. we can see some general information. Specifically, we can see where the intercepts are. We can also see that we have 3 local extrema. We have a local minimum here, somewhere between -2 and 3, not necessarily halfway in between them. We have a local maximum somewhere here between -2 and 0. It might occur at -1, but it might not. And we have a local minimum somewhere between x equals 0 and x equals 3. So in this case, we see that we have 3 extrema, that is 3 turning points, which is the maximum number that we could ever get out of a degree 4 polynomial function. And therefore, that gives us the graph, or a sketch of the graph of this polynomial function. Our last topic for today is one that can help us determine something about where the zeros of a function are. That is, the x-intercepts of a function, even when we can't factor it or work out its zeros some other way, say by using the quadratic formula. This theorem applies to all continuous functions, of which polynomial functions are a type. And it says that if I've got 2 inputs, x1 and x2, and there's some y value that lies between f of x1 and f of x2, that is the outputs that you get when you plug those 2 inputs in, then there has to be some point in between x1 and x2, some point b, so that when you plug b into the function f, the output is c. This is easiest to see when using a graph. So we've got the general situation sketched out here, where we've got x1 and x2 on the x-axis, and let's say that we've got the 2 blue points noted here, and we know that the output of the function at x1 is some value, f of x1, and the output of the function at x2 is some value, f of x2. And now I'm going to try to sketch in what the graph of this function might look like. And there are lots of different ways that that could go. The function could do something like that. It could go up and around like this. It could go very directly. It can go way down here and then come back up. But notice that in any of these cases, oh, that one was a problem. Notice that in any of these cases, because my function is continuous, because the graph of f has to be made in one continuous motion, or has to be able to be made in one continuous motion, no matter what, I'm always crossing this horizontal line at C somewhere, because that horizontal line, which has the equation y equals c, lies between lies above one of the outputs and below another one of the outputs. And so no matter what, I'm always going to be able to find some x value that has c as its corresponding y value. So some of the possible values of b are down here. And all of these b's that we have, notice, are between x1 and x2. There always has to be some input between x1 and x2 that has c as its corresponding output. Now, there are lots of things that we can do with the intermediate value theorem. We're going to be looking at one particular application, which is the following. If we've got the function f, and if we've got 2 different outputs of it, one of them being negative and one of them being positive, then there has to be an x-intercept, a 0 of the function, between x1 and x2. So if you ever have a function, or a polynomial function, and you evaluate that function at 2 different numbers, and one of the outputs is positive and one of the outputs is negative, then you know that there has to be some x-intercept of the function lying between those 2 inputs. Let's apply this to an example. Let's show that there exists an x-intercept of the function f of x equals 5x to the fifth minus 4x to the fourth plus 3x cubed plus x squared minus 1 somewhere between the inputs x equals 0 and x equals 1. This type of problem will always be handled in 2 steps. The first step is going to be evaluating f at 0 and 1. Well, at the 2 points that we believe are going to bound the x-intercept, that are going to be on either side of the x-intercept. So let's go ahead and do that. F of 0 will be 5 times 0 to the fifth minus 4 times 0 to the fourth plus 3 times 0 cubed plus 0 squared minus 1, which all works out to be -1. F of 1 is 5 times 1 to the fifth minus 4 times 1 to the fourth plus 3 times 1 cubed plus 1 squared minus 1, which gives us 5 minus 4 plus 3 plus 1 minus 1, which all winds up giving us 4. Step 2 is to check whether one of the numbers f0 and f of 0 and f of 1 are positive, is positive, and the other negative. If so, then the intermediate value theorem, which I'll abbreviate IVT, shows that there is an x-intercept between 0 and 1. So we have in fact shown that there is an x-intercept of this function between 0 and 1. Drawing the graph out isn't strictly necessary, but it is helpful for us to make sure that we have a good idea of what's going on. Oh, I didn't sketch that in very nicely. Go like that. Go -1. Actually, let me do -1 like this. 1, 2, 3, 4. So what we're told, or what we calculated in step 1, is that f of 0 is -1. That means that the point 0, -1 is on the graph of this function. Also, we have that the point 1, 4 is on the graph of this function because f of 1 is 4. So, just like we did before, we can imagine a bunch of various ways that we could try graphing the function, what the graph of the function between these 2 points looks like. But no matter what, all of these possible graphs cross the x-axis somewhere between 0 and 1 on the x-axis. And therefore, that shows that this function has an x-intercept between 0 and 1. Now, we don't know exactly what number it is, but one way that you could get more precise numbers is to try plugging in 1/2. And if you evaluate f of 1/2, you'll get some number out of that. And you can say, well, is that number positive or negative? If it's positive, then you know that the 0 has to be now between 0 and 1/2. But if it's negative, it has to be between 1/2 and 1. And because f of 0 is negative and f of 1 is positive, and if you just find 2 inputs where one's positive and one's negative, a 0 has to be between them. And you could narrow down your possibilities quite a lot by just evaluating the function at lots of different points inside, and you can get precise. But this process will never give you the exact x-intercept of the function, but in many applications, the approximation is all you need.